Greetings, everyone. This is Dennis Helsel, and today our webinar is testing groups of data with multiple detection limits. It's good to be with you again. And we'll begin. So today we're talking about testing groups of data with multiple detection limits. Our goal is to be able to test groups like you would with analysis of variance or with the Kruskal-Wallis test is the non-parametric test, but to handle data with detection limits and even data that have multiple detection limits. And another place to get more information on the topic, although we're doing some things today that are not in this book. This is the book that I wrote in 2012, Statistics for Censored Environmental Data using Minitab and R. And in there, it does talk about the tests for determining whether the groups are different, but does not talk about the multiple comparison procedures, which groups are different from others. And we're going to talk about both of those today. And that's fairly recent in some newer packages in R. But you can go to that book for some more information. So there are a variety of methods for testing differences between groups. They fall into two primarily classes. First one being parametric tests. You're probably familiar with these. These test differences in group means. So does one group have a higher mean than another group would be the question that it asks, much like the analysis of variance question. And you must designate that the assumed distribution that hopefully best matches the shape of your data is the one that you're using as an assumption. These tests are run with something called maximum likelihood estimation, a different way of computing it with censored data than they are with analysis of variance, but they're very much the same idea and they have the same assumptions. They would assume that the data in each group have that particular distribution, such as a normal distribution. That's the assumption for analysis of variance, although that distribution does not fit data with nondetects very well. And in addition to that, there's an equal variance assumption, just like with analysis of variance, that each group has the same variability. Both of those assumptions are usually violated pretty strongly with environmental data, and especially data with nondetects. Data with nondetects are down close to zero. Zero is a brick wall, a bottom line that we can't go below, at least for most things that we measure. They don't go negative. That introduces skewness. If the data are skewed, they are not a normal distribution. So usually we would choose a distribution for these parametric tests that is not a normal distribution, the most common being log normal or gamma. And the way to look at those is, we'll see, but looking at Q plots or probability plots and see which ones fit best. The second type of class, the second class of, let me try it again. The second class of the methods is non-parametric tests. And these tests do not assume a distribution and they do not assume equal variance. They're testing something different. They're not testing differences in means. They're testing differences in the cumulative distribution functions or set of percentiles for the data. So they're asking the question, does one group get shifted higher than another? So that its median is higher, its 75th percentile is higher than the equivalent statistic in the other groups. So those are the two classes of procedures we're going to talk about, and we are going to look at both of them. The data today I'll use is from the Ontario Pollen Monitoring Network. And so there they've looked at pesticide concentrations in pollen at beehives across the province. And there are pesticides of interest. These pesticides, the class is, let me see if I can get it right, neonicotinoids, related to nicotine, I believe. And they're neurotoxins so that they kill insects by damaging their nerve system. And unfortunately, they're not real selective in what it does with different types of insects. And so the concern is the effect on honeybees here. And corn seed and soybean seed are very often treated with these pesticides. And one of the pesticides is thiomethoxam. And so we will look at that today. And we'd like to know whether the concentrations differ between the 4 stages of plant growth: pre-plant, post-plant, when the corn tassel is out, and goldenrod. So the source here is the Ontario Ministry of Environment, and there's a web page, I should have it up here, but it's not there, I see on the slide, that tells you where you can go to get this information. How would we read in data with nondetects? To start with, on the left-hand side, and I don't see my cursor working, so I don't know whether you can see it, but on the left-hand side are in purple the way that we might have our data recorded, less than 0.05. So that's a detection limit. This data set has 1 detection limit, but it very well could have more than 1 for the types of methods that we're going to use, because those methods that we're going to be using today handle multiple detection limits. So you read it in as less than 0.05, that's a text variable, and it would be that way in Excel in perhaps the original data form. It would see that as a character variable because of the less than sign. When you read it into any statistics package, it would read it in as a character variable, and we cannot do statistics on character variables. So how do you read in data with nondetects? Well, you do that by putting them into 2 different columns. And so this is called the indicator column format. It is one of 2 common formats that statistics software can use, and you can read about the 2 formats in that textbook that I flashed up there, the Statistical Methods for Censored Data textbook. And so this is one of them, the indicator column format. The first column, which is the thiomethoxam column, are concentrations, and they're either detected concentrations or they're the level of the detection limit itself. So in the first row, we've got a 0.05 for the less than 0.05. In the third row, we've got a detected 0.86 parts per billion. Then the second column is an indicator that tells you which is which are detected, which are detection limits. And so there's a 1 here in that second column, that's the thiocens column. 1 means true in computer jargon. So 1 means true, and so this is true that this is a censored value, that this is a non-detect. So it's a less than 0.05. Down in the third row, there's a 0 there. That 0 means false. So that means this is not a censored value. It's a detected value at 0.86. So those are the 2 columns that we need in order to represent this. The third column, called sampling event, is a character variable. It's just a set of text. The first row is 3 dot space corn tassel. So it's the grouping variable, and we're going to split the data up into these groups and then test to see if the values of thiomethoxam are the same generally in all of the groups, or whether some groups are different than others. So to do a parametric test, we would compute do a plot of a QQ plot, or probability plot. Here the distribution is represented by the straight line. This is a normal QQ plot, so we're comparing data to a normal distribution. And this was the subject of last month's webinar, which you can go to the practicalstats.teachable.com site and hear for free. That's the recording of the webinar from last month. And it goes over these plots and how to fit data using these plots. But basically, you're going to look at the pattern of the data. And here the data are smiling at you. And so the data smiling at you is the data are telling you, if you're looking for a good match, if you're looking for a dating website for data, then I'm not a very good match for you. That's what it's saying. This is not, the normal distribution is not a good match for the data set that we've just put in here. And the circles here are the detected values. Non-detects are not plotted because we don't have values for the non-detects, so we don't want to impose one. We don't want to substitute one in. But they are represented in the spaces on the plot. So for example, towards the left-hand side of the plot, values for the x-axis of about a -1.3 or so. That's representing the lower part of the data set, and you see that the data don't start. The first value, which is just looks like the Y value, which is the concentrations, are just above 0. They're just above 0.05 actually as being detected. The quantiles, the x-axis, are the quantiles of the distribution, in this case, the normal distribution. And for a normal distribution, the mean for these standardized quantiles, the mean is at 0, and the units are plus and minus 1 or 2 standard deviations. And so the data below about 1.3 standard deviations below the mean, which is probably about the lower 25% or so of the data, are less than 0.05. So they don't show here, but their space is preserved. And so the percentile values, the quantile values here, for the detected values are correct in that they show that there's about 25% of the data below the first detected value. And if there are multiple detection limits, those spaces are interspersed where the data are here, where the data are shown here. So the non-detects are influencing the percentiles, the CDFs of this data set. And that will affect a mean, and it will also affect the percentiles themselves, depending on whether we're using a parametric or non-parametric type of procedure. So if the data are curved, just to summarize, you're not fitting this distribution very well, you could do an official test like the Shapiro-Wilk test and find out that you would reject normality with this data. Here's a log normal probability plot. So it's the logs on the y-axis of the concentrations that are plotted. I've kind of obscured the plot a little bit with text. I generally don't do that. It's not generally a good idea, but just to demonstrate again that with this arrow on the left side, the purple arrow, that's the space that the data below the lowest, or in this case, the only detection limit are occupying. And then if you had multiple detection limits, there would be non-detects interspersed with the positions where the circles are as far as their space, but they wouldn't be shown because we don't have a number for them. But they would account for the spacing of the detected values. So that's how non-detects influence these plots and also the methods, the procedures that we're going to use in a moment. So these concentrations are skewed, something like a log normal, which means that when you do box plots, the top part of the box looks bigger than the bottom part of the box, looks taller. Here are the 4 groups, and you can see that they certainly appear to look different with higher values in the pre-plant and post-plant groups, and lower values, mostly less than 0.05s, in the corn tassel and the goldenrod group. This is the command to get this censored box plot, the sen box plot command, which is part of the NADA package, NADA. The first version of that book that I showed you was named Non-Detects and Data Analysis, and this package in R, which is the NADA package, is based on that book. It's not something that I wrote, and I don't have any ability to change it. There are some things in the NADA package I would like to change, and some things that we'll talk about today that I would love to add to that package, but I'm not able to do that. I'll show you how you can get around that today. So this is the command to get that box plot. And we could plot the logs instead of the original data, so this is on the log scale. So again, we would expect from the plots that these groups look different, and we're going to find out that they in fact are. I won't go into it in detail. I've done it many times before in many places, but if you substitute it in numbers, like half the detection limit for these, you'd very likely not see differences between these groups. It's a great way to obscure data, and that's not something we want to do. So don't put in a half the detection limit or 2/3 or the detection limit itself or zeros. You're putting in data that all say that all of those numbers are the same, and you don't know that. The statistics software doesn't know that you don't know that. And so it's going to count all of those as evidence for being exactly the same. And that's not true. So we want to do something better than that. All right, before I go to the description of what the parametric method is, maximum likelihood, I'd like to find out a little bit more about you. And so I'm going to do a poll. Don't usually do this, but I will today. And so I would like you to respond with one of these answers to the question, to analyze data with nondetects. What I've done is, and so you've got 4 options here: to substitute a half the detection limit and then run the standard test like analysis of variance, to use non-parametric tests and rank all of the nondetects as the lowest data, to use the NADA package or something similar that actually is built for these things called censored data, data with nondetects, or give up. I'll give you a minute or 2 to decide which of those things. It shouldn't take long, and I don't want to use up a lot of the time, but give you just a second more. Okay. So you should see here that looks like not quite half, 45% people said that they would analyze the data using the NADA package or something similar, and that's great. That would not have been that high of a percentage 5 years ago or 10 years ago, even though the package existed back then. So I'm glad the message has gone out. And then about a quarter of the people substituted 1/2, and a quarter of people used non-parametric tests. Both of those have issues compared to using the things we're going to talk about today. The people that substitute, it's, as I said before, a great way to not find differences. In other words, it's not a good method. It really doesn't capture the information that's in the data, and it puts in information, quote unquote, that is wrong. And so it's not something you should do ever. Calling all of the nondetects the lowest value and using the non-parametric tests is a wonderful procedure if you have one detection limit, because you know that all of the nondetects are the lowest values in the data set. And so they can be ranked, they'll be tied with each other, and it's a great procedure with one detection limit. But with multiple detection limits, it's really not correct. If you had something like, instead of just 0.05, if we had 0.05 and 0.10, and there might be a value that's less than 0.1, that's really a 0.07, and it's higher than the 0.05s. And so if we call it the same as the 0.05s, we've not gotten it quite correct. So these censored procedures have advantage over both of the first two, and they certainly do have an advantage over giving up. There weren't too many people, but there were a few that were honest and said they gave up. And that's certainly understandable, except that these days there are methods to handle this. So we're going to talk about them right now. So let's start with the parametric method called maximum likelihood estimation. So what maximum likelihood estimation does is it starts with the data, that's the truth, including nondetects, because nondetects are part of your data. The worst thing you could do ever is to throw those away. You're just throwing away the low end of the data set and making some statement about the higher percent of your data. And you would never do that if you had numbers down there. Don't do it when you have less thans down there either. So we'll start with the observed data, and then your choice of which distribution should be used. I'm going to use the log normal, since that's what looked like it was a pretty good fit from the Q plot. Given that data, what are the parameters for the mean and the standard deviation for that distribution? So the normal and log normal use the mean and standard deviation as their parameters. Gamma has other parameters, but it's the same idea. So you're fitting a smooth curve to your data, basically. And so which fit is most likely to have given rise to the data, to your observations? That's what you want to know. And so you can solve for that using optimization, where the values for the parameters, in this case the mean and the standard deviation, are varied, and then some measure of the goodness of fit, or actually in this case the badness of fit, between the observed data and the parameters are computed. And so what the maximum likelihood does is find the minimum measure of bad fit. It's something called the log likelihood. And the log likelihood is a measure of error. And so it's going to vary the values for mean and standard deviation, compute the log likelihood, and find the one that's the lowest. And you can't get any lower than that. It can't get any better than that. And so that becomes the maximum likelihood estimates for the mean and standard deviation. In the process, no values are substituted for non-detects. There's no not 1/2's put in or 1's put in or 0's put in or anything else. Instead, it's fitting really two parts. There's two parts to these likelihood functions that produce the log likelihood. And the first part is the fit to the observed detected observation, so you can fit that to the concentrations themselves. The second part is a fit to the proportions of data that are below each detection limit. So in this case, if there were 25% of the data that were below 0.05, less than 0.05, we want to come up with a solution that has pretty close to 25% of its values below 0.05. So it's that percentage information below one of maybe 8 different, or how many ever different detection limits you have. You want to fit those proportions correctly. So the information provided by non-detects is in the observed percent below each detection limits. So for example, if there were 2 detection limits at 0.05 and 0.10, the percent below 0.05 would just be the number of values recorded as less than 0.05 divided by n. And you'd want to come close to that in your fit. You'd want the computer to come close to that. And then the percent less than 0.10 would be the sum of the number that were less than 0.05. We can count those, plus the sum of the number that were less than 0.10. We can count those, plus the number of detects that were between 0.05 and 0.10. So from 0.05 up to just below 0.10. That would be the number of values less than 0.10, and you divide by n, and you've got that percentage. So you'd fit those two percentages hopefully well. So that's how the information in any of these censored data procedures are used, without substituting values that you do not know for them and that you will get into big trouble for if you do substitute for them. So there's a log likelihood that's fit for a no model fit, or in other words, the null hypothesis, which is that all the group means are the same. All the group means are just slight noise variations around the overall mean of the entire data set. So there's no difference between the groups. So you can get an error measure back for that no model fit, no difference between groups, and then compute a log likelihood for the model fit based on fitting your data using these group assignments. And so we're going to get back a log likelihood for each. And there will be a statistic, the chi-squared statistic, that's computed as a -2 times the difference in the two log likelihoods. I won't go into today the reason why it's -2, and I found my cursor. So -2 times the difference in the two log likelihoods is a chi-squared statistic, and that statistic is a measure of the single signal strength for the difference in the means. So if that number is large, we're going to find out that the means are different and reject the null hypothesis of no difference. If the chi-squared statistic is small, there's not much evidence for a difference between these model log likelihood and the no model, all the same means log likelihood. If there's not much difference there, then it won't find a difference between the groups. All right, so this is an overall test. It doesn't tell you which group means differ from the others. It just tells you that there is a difference, that they're not all the same. And this is exactly analogous to analysis of variance, which is also that type of test, an overall test. So here is an MLE, and in quotes, ANOVA. It's not really an analysis of variance, but it's same idea in terms of the purpose of the objectives. This is on the logarithms. The command that I used is called sen ANOVA, which is something that I've written. It's one of those things I would like to have in the NADA package, but it's not there. So I'll tell you how to do it yourself. If you were taking our NADA course, you would get this and some other commands that I've written. If you don't take the course, that's fine. I'll try to show you as best I can what commands you would use, that this is using internally. So the sen ANOVA procedure, if you look at the output there, it says that the MLE test of the mean of the natural logs of the data, and the SENS data here is thiomethoxam, is split by the factor, which is sampling event. It assumes a log normal. In this case, you can change the command and say log equals false, I believe it is, or something like that, and you do it on the original data. Here's the chi-squared statistic, 146.3. That's a really big chi-squared statistic, and the p-value is extremely small, 10 to the minus 31. So there's 31 zeros in front of the number. So it's really small. So that's extremely a large amount of difference that the mean logs differ. And we're testing mean logs because we either took logs of the data, or we have assumed a log normal distribution, same thing. So what we're really testing are the geometric means. And those are very similar to an estimate of a median. So when you transform data, then you have to transform the interpretation of what you're doing. And parametric tests, if they're testing on difference in means, are testing on differences in those units. And here it's the units of logs. So here's the multiple comparison tests, and I'll tell you how it works in a little bit, but it's by Tukey contrast. So there's various kinds of multiple comparison procedures, and Tukey's is one of those. It's the standard one in parametric procedures. Each of these will be like a maximum likelihood estimate version of a t-test. And so it's comparing two groups. It's going to sequentially do two. If there are k groups, in this case k is 4, there's going to be k times k minus 1 over 2 comparisons, so that will make 6 here. And we do have 6 comparisons. So we have post-plant versus pre-plant, and the magnitude of the difference in the means is going to be 0.2197. Post-plant is smaller than pre-plant, so that's going to be negative. Is that different than 0 is what the procedure is estimating. The p-value is 0.9, which is much larger than 0.05, so it's saying that there's no evidence for difference in these two means, that this difference is just noise. The second one is corn tassel compared to pre-plant, and that's a minus 3.37. The p-value is very small. This is a very significant, it's a big chunk here, a big difference between the two means, and it sees those as being different. So when you end up with these, 4 of the 6 are significant, 2 are not significant. The 2 highest ones, post and pre, are not significant. The 2 lowest, corn, tassel, and goldenrod, are not significant from each other. So the pattern, this is what I've drawn in. Some software does this, it's not done here, where if it's given the same letter, the means are the same. So pre and post are the same. Corn tassel and goldenrod are the same, but any comparisons across that boundary are different. And that's a lot like what we saw with the box plots. So the multiple comparisons, for each comparison of two groups means, it computes that difference, checks to see if that difference is significantly different than 0, gives you back a p-value for that. The thing about multiple comparisons is that we had to do 6 of these in this case. We're going to have to do k times k minus 1 over 2 of them. If we just did each one at a value of 0.05 for our alpha, our cutoff for where we decide significance, then there's going to be more than a 5% chance once we've done 6 of them that we've made a mistake, that we've declared them to be different when they are not different. And so what we want to do is minimize the total mistakes, or what I'd call the pattern error rate. It's usually called the family error rate in statistics. And so it's this pattern of A, then B, B, and which ones are different and which ones are similar. I want that to be a 5% error rate. So it takes each of these individual comparisons, all this is done in the software for you, and tests that at a lower than alpha of 0.05. So it's going to look for differences, and they'll be significant perhaps if they're below 0.01 and smaller. But then what it does at the end, because this is a multiple comparison procedure, it's going to scale it back up here when it presents the p-values to you, so that these p-values represent the pattern error rate. So you can just use 0.05 as your cutoff as usual for here. So it gives you these 4 that are significant, 2 that are not. So that's Tukey's multiple comparison test, and it's one of the best multiple comparison tests in a parametric mode. It has the same assumptions of each group has a normal distribution and have the same variance. And our data usually don't fit that. So it's not the best way. So here is if you were not using the ANOVA command that I mentioned, that I've written. The ANOVA kind of procedure is based on the servreg command. That's a command in the survival package of R. The survival package is part of the base package of R. When you load in R, before you add any extra packages in, you've already got the survival package. So all of these censored data, at least the basic censored data methods, are in the survival package. And then the multiple comparisons are in one of these newer add-on packages. It's called the multcomp for multiple comparisons, the multcomp package, which has a whole host of different kinds of multiple comparisons procedures in it, including ones for censored data. So the GLHT command, I believe that stands for Generalized Linear Hypothesis Test command. So it's a general command that does a whole large number of different kinds of these parametric multiple comparisons. So those are the 2 commands that are used inside ANOVA. So that's the parametric approach, and we found differences between these groups without substituting any numbers for the non-detects. And it can handle many more than one detection limit if you have more than one. The non-parametric approach, which we're just about to do, is called SAN1-way, something that I've written, but it's based on these commands. It's the overall test, which would be very equivalent to the Kruskal-Wallis test, except handling multiple detection limits, is in the servdiff command in their survival package. So it's the difference, it's a test for differences in the CDFs of groups to see if they're all the same or whether at least one is different, just like Kruskal-Wallis. And then there are multiple comparisons. It's in something called a newer package, the servminor package, which is just pairwise underscore servdiff. So it's going to be doing a whole sequence of these servdiff commands, tests, but just splitting out the data into 2 groups at a time and doing it for all the possible 2 group combinations. So that's the pairwise servdiff, and it again does adjust for these multiple comparison p-value things so that you get an overall 0.05 error rate at the end. And I'll be using the BH correction, which is one of the newer corrections, stands for Benjamini and Hochberg, the 2 people that developed it in the late 1980s. If you have not heard of that adjustment, it's available for parametric as well as non-parametric methods. If you're not familiar with the BH adjustment, sometimes it's called the false discovery rate, different name for the same thing. It was developed in the late 1980s, so it's fairly new statistics-wise, at least as those methods filter down into environmental science. You should get familiar with it. It's really the best at this point, the one with the most power. So in SAN1-way, this servdiff command runs a variety of these kinds of tests, and the one I'm using here is called the Pareto test. It's a non-parametric test. It is a maximum likelihood kind of procedure. It's going to compute scores, which are a lot like ranks or percentiles, and it will have scores for the uncensored data, and it does calculate scores for the censored non-detect data. The tied values, all the less than 0.05s, will have the same score, but it preserves the idea that they're less than the rest of the data. Data in between, mixed in between, are going to get these scores based on what it knows, and what it knows is based on the percent of data below the detection limit that it's listed as. If it's less than 0.10, it'll have a different score than a less than 0.05 does. And I won't go in today into how that is done, but it's a standard procedure in censored data. It's been around for decades. So from these scores are computed a log likelihood, again, a measure of fit or misfit, actually, using the detects and the non-detects. And so this error is a function of both of those. So we incorporate the information that's in both, but we do that without substituting in a number for the non-detects. And the log likelihood with group differences is compared, again, to the log likelihood for the no group differences. And if there's a big decrease in the error, a decrease in the log likelihood with the model, with the group differences, that's a better model. And so if the lower log likelihood is a big difference, then the model is important. The model is not just the null hypothesis, not just saying that there's just noise around all of the group means. It's saying that the group means really do differ. So if the group difference model has a significantly lower error than the null model, the p-value is small, the group assignment is explaining at least part of the variation of the data, a significant part, and we're going to reject the null hypothesis. So there are different ways to compute these scores that people have developed over the years. The Pareto test and the Tyrone-Ware tests really are the ones that have the most power in general for the kinds of data that we have, which are data that are shaped, skewed, something like a log normal or a gamma distribution. The log rank test is another one of these that you'll see in software that's not as powerful. It is what is used in medical statistics, but then they're usually dealing with data that don't have the same shape as the data that we're dealing with. So a chi-squared statistic is again computed as the 2 times the difference in the log likelihoods, one with a model, one with no model, one with group differences, one without group differences. And the difference in that to those 2 log likelihoods, if it's big, a big difference, it means that the model, the group differences, has explained a lot of the variation in the data. And so we are going to get a big chi-squared statistic in that case, which gives us a small p-value. And so we would reject the null hypothesis that the groups are all the same. So if there's a big effect, we'll get a small p-value and reject the null hypothesis that there's no difference between the CDFs, the set of percentiles in the groups. And again, like the Kruskal-Wallis test, this is an overall test. There's no statement of which group this should not say means. Which group CDFs differ from others? I must have copied and pasted incorrectly here. I'm sorry. No, there's no statement of which groups differ from the others in their percentiles. That's done with multiple comparisons. So this is the send one-way command. You'd plug in just the concentration column, the censoring indicator column, and the group. And it gives you back the one-way test of the censored data by the factor of group, which is sampling event. 127 is also a big chi-squared, a huge one, 10 to the minus 27th p-value. So we just strongly reject the null hypothesis that all the groups have the same percentiles. Some of the groups are going to be shifted up compared to the others. And then we can do pairwise comparisons using that pairwise underscore servdiff command that I talked about earlier. And that is done here. The p-values here are arranged in a triangle, but it's the same idea. They are counting for the multiple comparisons that we're doing 6 of them here. And they're scaled so that when you read it, you can just compare it to a 0.05. It's giving you back the p-values for the combination of all the possible differences. It finds that the post and the plant, the post plant versus the pre-plant, 0.416, they're not different. The other 4 going across the different types of groups that we saw before are again strongly significant. And at the low end, the corn tassel and goldenrod are almost significant. If you're at a 0.05 level, that's enough for me to say I'd better look at that and see. So officially, the B's are the same here, but they're almost different. There's slightly more power in this because we're not making any assumptions of normality or equivariance. Here's one way to plot those. This is the CDFs themselves, the cumulative distribution functions, which is a step function. And these step functions jump at every detected observation. Log scale of concentration on the x-axis, the y-scale is the percentile or quantile value. So a median would be at 0.5 here. You can see from these CDFs, we're not seeing anything. We're not seeing anything below 0.05 because it's not going to tell you anything other than that at the lowest detection limit, the percentile is going to be right here. So about 10%, 0.1, about 10% of the observations in those two groups are less than 0.05. And then the detects start at that point. And these two, the upper two, the pre-plant and post-plant, look pretty similar in their CDFs. And so they're not declared different. Here is the CDF for corn tassel. The first time we see a detect there is about at the 70th percentile. So there's about 70% of values below 0.05 there. And with the final group, the goldenrod group, it's about 85% non-detects, values below 0.05. So those are the four groups. The parametric test did not find those to be different. The non-parametric test almost did find those set of percentiles different. And the non-parametric test is saying is 85% less than 0.05, different than 70% less than 0.05. That's the kind of information the non-detects are using or providing. Here's the same data again, plotted on a log scale with box plots. And just to show you that same idea, for the top two groups, the 0.05 detection limit here is around the 10th percentile. You don't really know where it is except that it's below the 25th. There are fewer percentiles specified on a box plot than they are on the CDF, but if you're trying to communicate certainly this with the general public, this is probably a better graph to use. So the 10th percentile there, it's about at the 70th percentile, somewhere just slightly below the top of the box. Corn tassel group, and it's actually above the top of the box here in the goldenrod group, so it's about at the 85th percentile. Okay, so that's how you would plot the data. So in conclusion, there are hypothesis test methods that are available for sensor data without substituting fabricated values. That's the word I use for sticking in a number for the non-detects. These survival analysis methods, that's the statistics jargon for them, work well for both one and multiple detection limits. They've been using them in medical statistics and other disciplines for decades. You can use parametric methods if you want to test for differences in means, and you're pretty confident you can fit a distribution to the data well. In this case, the log norm will fit really well, and I would have plenty of confidence that the means are different here. We've met those assumptions pretty well here. With the non-parametric methods, you don't have to make those assumptions. It tests for a different thing, though. So the big difference in choice of whether you use a parametric or a non-parametric method, whether you're talking about data with non-detects or data that don't have any non-detects, the deciding factor really is not, do my data look like a normal distribution? It's, what am I trying to do? Am I trying to test for differences in means? Or I'm trying to test for whether there are differences in, does one group give me bigger or smaller numbers than other groups? That last statement is what non-parametric tests do. Has there been a shift? So if you want to use a non-parametric method to test for a shift, generally higher values in one group than another, that's what they do, and you don't have to worry about the distribution, which in my opinion is a big plus. And there are multiple comparison tests available for both types, both categories of these methods to follow up with and determine which groups are different from the others. Okay, so you have some questions. I'm going to try to answer them as best I can. All right, so how do you deal with data that have upper limits and lower limits? Justine, great question. There is one of our newsletters that handled that. It's really not the topic today, but these sensor data methods can handle both. You have to input the data slightly differently and tell it which ones are higher than the limit and which ones are lower than the limit, but you can have censoring on both sides. So those kind of things are available in that survival package in R. Okay, and there's a little bit about that again on an example of how to do that in one of our newsletters. That's on the newsletter, in the newsletter archive. How would you go about creating your own code or function? So Kate, all the Functions are that you write, they're called scripts in R, are just a series of commands. So if you can type it, if you can type in the command, you just collect those commands together. And you have to put in a line right at the top that tells it that it's going to be a function, and then a bracket that encloses all the commands, and then an end bracket at the end, and you've got a function. So it's not that difficult. There's a lot online. I would send you to the CRAN site, the CRAN site, which is where all of the R stuff is. There's plenty of information there on how to build scripts. It's all free information on how to build scripts. Good. Someone from Thailand. The intent of some of these webinars and the courses are me being able to present information to people over the world, and not just in North America, so we can defeat the time zone thing. But thank you for being on the webinar, and it's certainly probably an odd time for you. Are multiple detection limits related to using different test methods with the same data? No. So multiple detection limits are simply, obviously they're a function of the laboratory, and they, at different times or with different methods or with different interferences in the laboratory. There are interferences in some samples which require the sample that you submit to the lab to be diluted, which increases the detection limit. So there's a variety of reasons, and by substituting in a half, for example, you're putting in a pattern that has nothing to do with the concentrations. It has everything to do with those changes and what caused the multiple detection limits. So that may be just over time. So you have a pattern of 1/2 the detection limits going down over time. That's not a good thing because it has nothing to do with what was in your samples. It's a great way to put in a downtrend that's not there, just as one example. So it's it is related to different conditions in the laboratory, which could have changed over time, could change sample to sample depending on the interferences and what else is in the sample that you send to the lab. And there's a big discussion of that in that textbook that I mentioned. Last question that I'll get to here, and the slide that says that it uses 1s and 0s for the indicator. Does R need true and false? Well, you could input data that were just text. You could input things like blanks for, let's say, the non-detects, and for the detects, and a less than value for non-detects. And then it's only one line to translate that into 1s and 0s. Does R need 1s and 0s? What R really needs is true and false. But most commands in R are written so that if you give it 1 and 0s for something that it wants true and false, it will just go ahead and translate that for you. There was a slide early on, it was the sen boxplot slide, that showed a function called as.logical, because the sen boxplot command does not do that translation for you. The things that I've written do. Most of the stuff that's written in packages in R are that way. At least some, if not all, of the routines in the NADA package do not do that translation for you. That's one of the things I would like to see changed. So if you put in 1s and 0s, and you really need trues and falses, which you do, the way to get that is with this text command called as.logical. And that's back on one of those early slides. Sorry, I couldn't get to all of the questions verbally, but with that, I'll say, hope you join us next month. Bye-bye.